Hi everyone, this is the second part of the video on on this lesson, properties of sound. In the previous video, I talked through amplitude and how I would take one tuning fork, this one, and I would tap it first and then whack it the next time to illustrate this concept of amplitude. And it's really about linking the physical movement of the tap or the whack with the sound that's heard, and then explaining that difference in terms of this abstract model of particles and disturbances and medium and oscillation and so on. So what I'm going to do next is think about frequency. So in this case, I'm going to take two different tuning forks. I'm going to take the biggest that I've got and the smallest that I've got. I should say at this point, by the way, many thanks to Gloucester Academy. They lent me these tuning forks. Yeah, it's very handy to have these. I wouldn't usually have these at home, but I'm sure you've got tuning forks in your prep room somewhere. So if you take these two tuning forks, and students can see firstly that this one is much bigger than this one. That's really obvious. You can also show them this. If I can just get these both in the light, that would be great. Yeah, so hopefully you can see here, this big one, it says 256 on, and the little one says 512. And what you can do, I mean, you can just tell them straight up. What that means is this one oscillates at 256 times every second. This one oscillates 512 times every second. And what we're going to do, and this is quite tricky, so, you know, there's a certain amount of just telling them, but we're going to try and explain to students why that is. So what I'm going to do, as we said in the previous video, we only want to change one thing here. So in this case, we've changed the length of the tuning fork. So it's really important that when we strike the tuning forks, that we try and strike them with the same amount of energy. So it's not we tap one and we whack the other. We want them to have approximately the same volume of sound. Now that is quite difficult to do in a kind of rigorous way when you're demonstrating this in the lab, but talk through it to students and just emphasize that you're trying to get the same volume of notes, but there is going to be a difference, as you probably know already, in terms of the pitch. So I'm just going to try and do a sort of a medium, I don't know what the word is for something between a tap and a whack. So I'll do the original one first. So you can hear that note and you can kind of show them that oscillation there, it's vibrating a bit or whatever. And then I'm going to do the same, approximately the same same level of striking with the smaller fork. Now hopefully they can see firstly, or they can hear firstly, that it's a much higher pitched sound. So that's important. The main thing is that they associate low pitched sound with the big one, high pitched sound with the small one. But hopefully what you saw there, maybe if I strike them both together, is one seems to oscillate a bit more than the other, and it's quite hard to see this, so you might need to do this a few times if I just have another go. So let's try one more time. It's pretty hard to see, but what you want to illustrate, unless you whack both of them and you can really get some vibrations, but what you want to illustrate is that because of that difference in length, you get some sort of difference in oscillation. So what I'm going to do is start off with the large fork. And I'm going to show this in a diagram, so let's draw the large fork in the diagram, just like those diagrams we've been doing. So this is my large tuning fork. And what you want to show is that the oscillations, the kind of magnitude of the oscillations is the same in both cases. Now again, I'm not sure how to draw this, and if you watch this video and think, George, your science is completely wrong, please do get in touch with me and let me know, because there's probably better ways of doing this, and again, you might want to find animations and stuff as well, that might be easier. But I do quite like how visual this is with the tuning forks. You can really relate the size to the sound. But if I zoom in on what's going on here, I think that the way I've done this in the past is to say, well, because this is a bit longer, if this is the original position of my tuning fork, this one, to oscillate by the same amount, has to kind of go quite a long way, like that, and the whole journey just takes a bit longer because it's a larger tuning fork. So I might put something here about larger fork, well, what we're thinking about in the abstract is this is a longer time taken to do an oscillation. So I'm just going to put longer time taken. Let's think about the small fork then. How is that different? And again, this is not the easiest to draw, but I'm having a go. And if you come up with a better way, that would be great if you could let me know. So let's really exaggerate here. Let's draw a smaller fork here like this. Now what we want to do is match the size of the oscillation to the size of the oscillation here. And the reason for that is because we want to keep amplitude the same. We don't want students, that is the worst thing that could happen, to be confusing the kind of magnitude of the disturbance or the oscillations with what's going on in terms of frequency. So if I draw this here, and I'm going to really stress to students, we've struck them with the same intensity, so they're oscillating by the same amount. The disturbance, or the size of the disturbance is going to be the same in both cases. What's different here is that because this is a smaller fork, actually to get at the same angle, this one doesn't have to travel as far. So it doesn't have to travel as far. And I hope that's clear, that difference, that you can say, okay, because it doesn't have to travel as far, it's a shorter time taken. So I might put shorter time taken. And so there we've explained this kind of concrete difference in terms of something abstract. But now we need to relate it back to the concrete. And therefore, if it takes longer to do it, you might also say fewer oscillations every second, but I think at this point it's maybe easy to think in terms of time. We could say if it takes longer to do it, then you get a lower pitch or lower pitched sound, if I'm really being concrete about it. Lower pitched sound or a deeper sound. This, on the other hand, when it's got this shorter time taken, is a higher pitched sound. And just to relate this idea of time taken or time period to frequency, sorry, I don't know where the light is here. So that's my bigger one. That's 256. That one's 512. I might want to say something like this oscillates 512 times per second. This one oscillates at 256 times per second. So it's really, this is a nice way of stressing that link between time period and frequency and the sound that you actually hear. And the last thing that might be worth adding here is just, I'm going to be really honest here, it's something in the national curriculum and I didn't know where else to put it. It kind of makes sense to put it in here. But you could add something here to say, rather than saying 256 times per second, we can also write 256 hertz, and that just means 256 oscillations per second. 256 hertz. This would be 512 hertz. I'll write that down here. Yeah, you can just about see. And then you could add a note in here, or just tell students, because they're going to do this in the deliberate practice later, but you could say something about the range of human hearing, which is the lowest pitch sound that humans can hear is generally about 20 hertz. So something that oscillates 20 times per second, which is still relatively fast. We wouldn't be able to move our hand at 20 times per second, but that's quite a low frequency. The highest pitch sound that any human can hear is around 20,000 hertz or 20 kilohertz, and you might want to add that as people get older, their hearing range maybe decreases a little bit, and so on. You could say something about dogs as well, hearing higher pitch sounds again. But that's just one thing that you could add in here when you're introducing this idea of frequency and how that relates to the kind of the qualities of the sound that we can hear. So that's just a simple way of illustrating it. You may come up with better ways, you may find animations which do the job better, but again, what we want through this lesson, just to reiterate, and I should add the word frequency in here, so what we're talking about here is a frequency, and you could add a label for the other one as well. But what we want is that students can think in terms of these two words, amplitude and frequency, and that they can view the world, or in this case, listen to the sounds that they hear and think about them in terms of those new concepts. So in the next lesson, we'll be mapping what we've drawn here, and this is really important, why we've drawn it out and gone the kind of long way around here. How do we then map that onto the sound wave traces that we'll look at in the next lesson?